Hello, I'm Timothy Helferstay, and the project that I'm presenting right now is the same one that we're doing for our 480 class, but there's a little bit of tweaks, and I actually added a little bit more than what we're actually doing for 480 to this just to make it a little more interesting. So the main background for this is there's a company called Nature Sunshine, and they're located down in Utah, and with one of their processes right now for their liquid production line, they actually have where they run all the product through, they fill it at about 190 degrees Fahrenheit, and then they have to actually take it off the line and store it in a warehouse for a few days while everything cools, and then they take it back, run it back on the production line, and have it labeled. Because if they do where they label it when it's still about 190 degrees, then when so the bottle expands, and when it starts to shrink down, it will mess up the label. So then that way it'll either fall off, get crooked, or if it's one of the adhesive labels that they stick on the front, it actually crinkles the label so you can't read it clearly. And since this obviously isn't a good solution, Nature Sunshine contacted us and had us come up with a different way to actually cool the bottles down, and that's what I'm going to go over really quick. This project was actually pretty straightforward, pretty simple. Um, with our 480 project, we're actually not using any sort of fans with it, but just for this one, we're using fans just to show how it actually affects the cooling time, which is a little different than what I would have previously anticipated. And we also use just some household items, a funnel, the bottle, and a measuring cup, and of course a shower head. As you can see from this graph, we have a few different volume flow rates, and with the low volume flow rate, it's actually about a quarter of the medium volume flow rate, and then the high volume flow rate is only about 5 times that of the low volume flow rate, which it seems like when you're looking at the low volume flow rate and the medium volume flow rate, that the cooling is actually really close, and at the end, the medium volume flow rate did take slightly longer to cool down the bottle than the low volume flow rate, and I'll be able to explain that later why I think that ended up happening. And then with the high volume flow rate, that one, as you can see, worked the best. It ended up cooling the bottles down to about 140 seconds, which is great. And for the low volume flow rate, went ahead and tested two different speeds with just used a box fan over the top, and that fan I had where I used the lowest setting, so the 1 and then the 3 for the high speed, just so there's a greater variance. And with the low speed, I found that it took quite a bit longer to cool it down. And with that, I think it's mostly because when the water was flowing over the bottle, instead of being effective and staying up against the bottle, the air was actually blowing it, so the less of the water was actually on the surface of the bottle, which since we know that the heat transfer coefficient for forced convection with liquids is a lot higher than it is for gases, it made it so a less efficient process was actually being done, or a less efficient fluid was being used on it instead of the water itself. And for the medium volume flow rate, we see the same trend that it cooled faster without having the fan there. And once again, I think that is the same issue going on, just having where that air is coming in contact with the outer surface as opposed to having the chilled water going on the and contacting the outside surface. Each method that was tested is far better than what Nature's Sunshine does currently. Even the control is quite a bit better and cools down much more rapidly than with Nature's Sunshine, and that's because with Nature's Sunshine there's an extra layer of resistance for it, and sometimes quite a few layers actually, because they do where they box all these bottles in the cardboard boxes that they're going to be shipped in, and they do where they stick them on a pallet, especially all of the bottles on the inside. They're not able to cool down quickly because you have all of that insulation between them and your T infinity, the outside temperature, and that causes it to just stay hot for a really long time. And if you look at the high volume flow rate, you'll see that even though it is about 1.25 times the medium flow rate, it cooled down much more rapidly, and that's because of all the contact it was able to get on the bottle. It was a larger diameter nozzle, so that way the velocity, it was a little slower than the medium flow rate, but yet the quantity of water that actually ran on the sides of the bottle was much greater. This is another just close-up view with the low volume flow rate and medium volume flow rate. And this is just so I can better explain why your volume flow rate isn't the only parameter that should really be taken into account when you're trying to figure out how fast something will cool. Just because you can have a great volume flow rate, but what actually stays on the side of the bottle or the surface that you want to be in contact with, that's what matters. And with the low volume flow rate, it seemed like it did a better job of actually staying on the bottle. The the medium volume flow rate, it had a higher velocity, and when it was hitting the bottle, a lot of it was actually kind of spraying off to the side instead of running down the bottle. And the low volume flow rate is at a lower velocity, and it was able to more of just trickle across the whole bottle as opposed to smacking into it and bouncing off. And that's why I believe that it cooled it down a little bit faster than the medium volume flow rate. Thank you.